All right, so we're the fifth place team. I'm Roger, and I'm joined by Junsung and Ian. Okay, so I had a BS in computational neuroscience from USC. I used to be a core contributor in the PyTorch Lightning project, and I was a RD engineer at a medical AI startup. And I basically joined this competition to learn about transformers since my previous experiences were all with, other neural networks. And here's Junsung. Junsung?
And I have a PS in the Korean University and MS in KAIST. And I'm currently working in Delta X, which is startup based on vision. And I also joined this competition to learn about transformers.
Okay, and Ian?
Hello, I'm Ian Zhang. I received my BS from Ina University, Department of Information and Communication Engineering, and I am currently studying for my MS from Ina University, Department of Electrical and Computer Engineering. I'm currently researching in the medical AI lab, and I participated in the Stanford Ribonanza RNA folding competition because it was interesting and something I wanted to experience it.
Okay, and yeah, we're just three random guys who joined on Kaggle, so we're not part of like any organizations or anything. And our model is basically a prototype encoder transformer using residual norm, which I don't think I've seen anyone else use. And we've added recurrent layers into our encoders as well. And we have been able to utilize pseudo labels, which is the semi-supervised part of our training. And for libraries, we use PyTorch, Lightning for training, Xformers for the attention function, and X transformers for the relative positional bias that we used. And for my model, it took about 2 days to train on a single 4090, Jinsung 7 days on a 4080, and 27 hours on two 4090s for Ion, since we each all had our own variations of the model. Yeah. And features selection and engineering. So for my part, I don't think we did too much in terms of feature engineering, except use BPP. For me, for my model, I used weighted sampling based on signal to noise. I didn't do any like log stuff. It was just linear, plugged straight in. And BPP provided the best performance when only the first half of the layers are injected. So I only injected BPP as an attention bias to the first 6 layers, as opposed to all 12 layers of the transformer. And the BPP is only passed through a single 1x1 2D convolution, which convolves it from a single channel to 6 heads. And BPPs can be refined further at the cost of training speed, which is, I think, what first place did. But I didn't do that because, well, limited time and compute. Yeah. I've tried adding contra BPP, which didn't help. Doing 3x3 com didn't help. Reducing the number of BPP heads didn't help. Using structure or loop didn't help either. And I think it might be possible to do multitask with BPP. I had tried a model that extracted the attention matrix from a single layer and attempted to do backpropagate BPP as an auxiliary loss, but that did not work as well as just simply using an attention bias injection. Yeah. Jinsung?
Me and Ian used sequence input and eternal BPP and SN to filter out some more noise samples. And signal to noise value larger than 0.6 sequences were selected. And we use, in contrast of the Roger, we use length match sampling based on the length of the sequences to accelerate training. And we used sequence embeddings multiplied by BPP passed through 1D convolution layers that has 3 and 7 kernel size. And what did not work was contra fold and R fold BPP, and also applying BPP features to partial transformer layers did not work, and excluding the targets in each sequences that has high error, as the previous open vaccine's first place solution did not work. And using more noisy samples, sometimes it worked and sometimes not. But in the final model, it did not work. And structural loop, we did not succeed to utilize that. Maybe what I'm thinking now is using weighted loss for the noise targets that use less weight for the more noise samples might work, but do not try in the competition.
All right. And regarding training methods, so we used a inverse square root error schedule, which you can see on the graph to the right, and with pretty short warm up. We used very high weight decay, 0.1, I think, pretty high, yeah. And we were able to make flip work with sequences as well as BPP. And for my model, I also augmented BPP with Gaussian noise, and that helped lower CV as well. And for the SM-weighted sampling part, I actually had it on a schedule so that more noisy data would be added as training goes on. Yeah, and the ensemble that we used for our final submission was basically 5 models, and each of them are basically like 5 folds. And for me, the ones from me that were used, one was trained with pseudo labels and one was not. Yeah. Shin-sung, Ian.
Okay. Is Ian's model, which is similar to my model. We did not use BPP values, BPP metrics to the attention directly, but we just extracted feature using 1D convolution, and we put that after the multi-app self-attention and feed-forward network to extract some features from that, and then we propagated through GRU layer, and it was encoder layer structure and last linear layer to extract the output. The calculation time of the models is as follows: total 27 hours for one model with 2 1490. And mine was similar to Ian, but just one change is encoder layer structure in the last. I just use one GRU and one LSTM with half hidden stage and just concatenate the vector to make it same size after the layers. And it has slightly worse private score, and I used tenfold, so I needed more time to train. And I also use it pseudo labels to train the models and then fine tuning.
Okay. I'll also talk about this part. So for our ensemble, basically Ian did all the weighting on this part. I'm not sure if I need to go over all this, but yeah, this was the composition of our submission, our ensemble. Important and interesting findings. So we had GRUs throughout in every encoder layer. So I think it reinforces the time and not time, but the sequential nature of RNA sequences. And I've tried residual GRUs, and they were always worse. I could not get them to work as well as just using GRUs straight up. And I think with squeeze formers or other models that use convolutional neural networks, the translational invariance that is offered by CNNs also helps constrain the solution space of transformers. And I think strided convolutions could possibly be used to capture longer range interactions, but I had not experimented that much with that. And I found that the residual norm architecture works rather well in preventing the model from going unstable, because I have tried pre-norm, post-norm, sandwich norm, and residual work the best. Yeah. And simple model. So out of the three of us, my model was the smallest. So I just put it here at the simple model part. And let's see. So for input, we only use sequence and BPP, and the signal to noise was only used for data sampling. And the BPP is only processed by a one-by-one convolution before getting added with the relative positional bias and then sent into the multi-head self-attention. And this model is 16 million parameters, and the times to train them are listed here. And the method used to train them is basically that we first generate pseudo labels. So I train 5 folds with Flip for about 28 hours on a single 4090. And then the models are discarded and only the pseudo labels are kept. And the pseudo labels are then filtered in the same way that the last vaccine competition, the first place, they set the predictions for they named out the predictions with standard deviation larger than a quantile 0.75. So that's what we use as well, and it has worked pretty well for us. And for the second stage, we basically only use the pseudo labels, so we don't use the train data at all. And we train the second stage, and it takes about 4.5 hours. And then from that, we take the checkpoint and then use it to train the 5 folds using the actual train data with no pseudo labels. And totally, it takes 2 days, and the inference is about 8 minutes per fold. Yeah. And that's it.